Hi, welcome to the fifth video in the rates and equilibrium topic. This video is going to cover what a reversible reaction is, how you can tell if a reaction is reversible, and what we mean by the term closed system. So let's start with a little bit of a recap about reactions. So most chemical reactions are ones that only actually move in one direction, okay? So they move from the reactants to the products. And we denote this by an arrow pointed in the direction that they are moving, that way, from left to right. So what that means is once A and B have reacted to become C and D, they can't ever go back to being A and B again. You would have to perform some other kind of reaction, or you may even need to split them using another chemical to be able to do that. But when we talk about these kinds of reactions, it's not feasible for them to just spontaneously become A and B again. So this is what we would call a normal reaction that you would see most often, those types of reactions that move in one direction, forwards. When we're talking about reversible reactions, however, what we're talking about here is that it can go in both directions. So that means that it can travel forwards and backwards. Now, some people refer to it as the backwards reaction, but quite often exam boards will call it the reverse reaction. So it's forwards and reverse. Think of it like a car. If you are moving from the reactants, so A and B, to the products, C and D, you are driving forwards down the road. But if you're going back from the products to the reactants, you are reversing back down the road. And what we do when we're talking about reversible reactions is we can denote that it's a reversible reaction by using half arrows. So what we mean by a half arrow is this symbol right here. So we have an arrow pointing forwards and an arrow pointing backwards. We do not put the full arrowhead on, so we don't draw this. That's incorrect. We draw this one here, a half arrow pointing that way and a half arrow pointing that way. That tells us that this is a reversible reaction. And this, depending on who you've been taught by in the past, this often is one of the reasons why we will not accept you putting an equal sign in an equation when we're talking about reactions, because this equal sign is very similar to that reversible reaction sign. So you might have been told by your teacher before that you should always use an arrow in your equations. That's the reason why, because if you were to write A plus B equals C plus D, you might make a mistake for this here, this symbol. So reversible reactions can go both forwards and backwards, and we use half arrows to show that they can do that. So they can go from being reactants to products, and then the products can go back to being the reactants again. So let's have a look at our reversible reactions in a little bit more detail. And the key word that you guys need to know about is this word here, equilibrium. And when we're talking about the equilibrium, we're talking about the rates being equal. What that means is if you have your forward rate, it is exactly equal to your reverse rate. So for example, if we had A plus B makes C plus D, for every one forwards, we would have one backwards. So if we had one molecule of A and one molecule of B, creating one molecule of C and one molecule of D, at the exact same time, we would have a molecule of C and a molecule of D becoming a molecule of A and a molecule of B. So we have these reactions happening together at the same rate. And that's what happens when a reversible reaction reaches equilibrium. The forwards rate is exactly the same as the reverse rate or the backwards rate. And if you look at this diagram here, this is a typical graph of a reversible reaction. So what you will see is that we have a high rate of reaction in the forwards reaction at the beginning. And this is because we have a high concentration of reactants. So there are lots of reactant molecules colliding with each other. Because there are more collisions, you get a higher rate of reaction. But what you should see is as the reaction happens, the reaction rate for the forwards reaction decreases because the reactants are being used up. And as that forwards reaction decreases, something happens with the reverse reaction, okay? And so what we should see here is that the concentration of products is increasing. It's actually getting higher because more reactants are becoming products. And as the concentration gets higher, we see a reaction rate for the backwards reaction or the reverse reaction increasing until they hit this point here. And this point here is equilibrium. And this is the point at which the forwards rate equals the reverse rate. And we can see that because both of the lines at this point right here are at the same point. They are overlapping each other because they are happening at the same rate. And that's what we talk about when we're talking about equilibrium. If you are asked a question about equilibrium in your exam, you should remember that it's the forwards rate is equal to the reverse rate. For every one reaction that happens in the forwards direction, you will get one reaction happening in the reverse direction at the same time. Okay, so how does temperature affect our reversible reactions? So just like we've seen previously, temperature will be dependent on whether a reaction is exothermic or endothermic. So if we have an exothermic forwards reaction, energy will be transferred from the reactant mixture to the surroundings as the products are formed. Now, exothermic reactions do not want to be heated. They don't require energy or an excess of energy to make them happen. And so if you were to heat the forwards reaction, you would actually slow it down. And what would happen is instead of the forwards reaction happening, the reverse reaction would happen. Because the reverse reaction is normally endothermic. So if we look at this diagram down here, what we've got is we've got A plus B making C plus D, and then C plus D making A plus B. The forwards reaction is exothermic, and it's exothermic because it releases energy as it happens, and we've denoted that with that red arrow. The reverse reaction is endothermic, and it's endothermic because it absorbs energy. And what that means is as the exothermic forwards reaction is happening and releasing energy, the endothermic reverse reaction is absorbing that energy and taking it in. And so what actually happens is we don't get an overall change in energy. So if you were to look at this again, if you have your exothermic reaction going in this direction and it released, say, 25 kilojoules of energy, at the same time as that, you will have your endothermic reaction going in this direction, and it will take in 25 kilojoules of energy. The reason for this, the reason why the exothermic reaction releases exactly the same amount of energy as the endothermic reaction takes in, is because they are breaking and forming the same number of bonds. So if you remember back to C7, we taught you about bond energy calculations and how every type of bond has a specific energy or enthalpy that allows that bond to either form or to break. And the formation and the breaking of that bond requires the same amount of energy. It either releases or takes it in. When we talk about these types of reaction, the exothermic reaction is going to produce the same amount of energy as the endothermic reaction is going to take in. So if we have an exothermic reaction releasing 25 kilojoules of energy, the endothermic reaction that happens in the opposite direction is going to take in 25 kilojoules of energy. And so what actually happens here is that we get no overall energy change. And the reason for that is because energy released is equal to energy absorbed. And if I add a little bit more detail here, this would be your forwards reaction, and this would be your reverse reaction. And the same would happen if it was the opposite way around. So if the forwards reaction was endothermic and the reverse reaction was exothermic, you would still have the same thing happening, remember? Because we're talking about this part here, the bond breaking and the bond formation. Okay, guys? So there are a couple of other keywords that you need to know about in this topic. The first one is this one here, closed system. So a closed system is one in which reactants or products cannot escape from it. So this is actually really important in meeting, or if I use a better word, in reaching equilibrium. So if you trap your reactants in a system, so it could be that you have a conical flask and you stick a bung in the top, like so. Your reactants are in here. If that bung is blocking them from getting out, then they will set up an equilibrium between them. And what that means is you will have the forwards reaction happening at the same time as the backwards reaction happening. And so you'll get this same rate between the two, and we'll get an equilibrium happening. Now, closed systems are really important in being able to show you how equilibrium happen and how reversible reactions happen as well. The second keyword that you guys need to know about is this term dynamic equilibrium. And so when we talk about dynamic equilibrium, we talk about the changing between products and reactants. So I've talked to you in previous parts of this video about equilibrium, and that if we have something that's in equilibrium, the forwards rate is equal to the reverse rate. Now, a dynamic equilibrium is actually talking about the change in the amounts of products and reactants. So when we talk about dynamic equilibrium, what we're looking for is there a change in how much product or reactant there is in the system? And when we reach dynamic equilibrium, that's a point at which there is no overall change in the amount of products or reactants. Okay, so if I was to say that we have A plus B and it's a reversible reaction that makes C plus D, if it's reached dynamic equilibrium, we might have 10A, 10B, and 5C and 5D. And what we mean by no overall change is no matter how many times the forwards reaction happens or the reverse reaction happens, we will always have 10A, 10B, 5C, and 5D. Those amounts will not change. Now, I've deliberately picked this example because a common misconception is that equilibrium or equilibria, if we're using the plural, will only happen if the amounts of A and B are the same as the amounts of C and D. An equilibrium for a reaction could happen at any point. It could be that you have more A and B, your reactants, than you do C and D, your products. Or it could be that you have more C and D, your products, than you do A and B, your reactants. It's not smack in the middle where you have 50% of the reaction mixture as reactants and 50% of the reaction mixture as products. It could be anywhere in there, as long as you have 10 and 10, 5 and 5. You could have 20 and 20 and 4 and 4. It doesn't matter, as long as when the forwards reaction happens, you still end up with 10, and the reverse reaction happens, you still end up with 5. And that's what dynamic equilibrium is. It's this no overall change in the amount of products or reactants in the system. They are always going to be the same. No matter how many times the forwards reaction happens or the backwards reaction happens, you will always end up with the same amounts of each of your reactants and products on each side of your reaction. They won't change. Okay, guys, so just a quick reminder of what you've done so far. We've looked at the fact that a reversible reaction is one which can travel in both directions. So we can go forwards and we can come back in the reverse direction. And because of that, we show it with a half arrow pointing forwards and a half arrow pointing backwards. Equilibrium is the point at which the forwards rate is equal to the reverse rate or the backwards rate. So if you have one forwards reaction, you will have one backwards reaction. And if we have a look at, in terms of energy, if we have an exothermic forwards reaction that released 25 kilojoules of energy, then the endothermic reverse reaction would absorb 25 kilojoules of energy. There would be no overall change. There's no change in the amount of energy in the surroundings. What is released is what is absorbed, because they are breaking and forming the same numbers of bonds. And then finally, the last part, dynamic equilibrium and equilibrium can only really happen if they are set up in a closed system. And a closed system prevents reactants or products from escaping, so that the reaction can actually reach its equilibrium, can have the same forwards and the same backwards rate. But what we need to remember is dynamic equilibrium is different to the equilibrium I taught you before. So standard equilibrium is that the forwards rate is equal to the reverse rate. Dynamic equilibrium looks at the overall change in the amount of products or reactants. And when we talk about dynamic equilibrium, there is no change. If you have 10 of each of your reactant molecules and 5 of each of your product molecules, no matter how many times your forwards reaction happens or your backwards reaction happens, you will always have those amounts if it is in dynamic equilibrium. And you need to remember that dynamic equilibrium will not be in the middle of the reaction. So there will not be 50% and 50% all of the time. It could be 50%, 50%, 40%, 60%, 20% and 80% in terms of your reaction mixture. Equilibrium is not defined by it being smack in the middle. Okay, guys, I will be back again very soon with another lesson on reversible reactions.